The idea that planets exist beyond our solar system is one of the most transformative discoveries in modern science. But for most of human history, it was nothing more than speculation. For centuries, people looked up at the night sky and saw stars as fixed points of light, distant suns that might or might not have worlds of their own. Philosophers and early scientists debated the possibility, but there was no way to confirm it. The universe appeared silent in this regard, offering no direct evidence that planets existed elsewhere. It was not until very recently in human history that this question moved from philosophy into measurable science, changing our understanding of the cosmos forever. The difficulty in finding planets outside our solar system is rooted in scale and light. Planets do not emit their own light. They only reflect the light of their host stars. Compared to a star, even a giant planet like Jupiter is extremely faint. From vast interstellar distances, a planet is essentially invisible next to the overwhelming brightness of its star. This makes direct observation incredibly challenging. Early astronomers understood this limitation, which is why for a long time exoplanets remained theoretical. The stars were visible, but their companions were hidden in their glare. Despite these challenges, scientists never stopped searching for indirect ways to detect planets. They reasoned that even if a planet could not be seen directly, it might still reveal its presence through its effects on its star. A planet exerts gravitational force on its star, causing the star to wobble slightly as both bodies orbit their common center of mass. This motion is extremely small, but it is measurable with precise instruments. This idea became one of the earliest methods used in the search for exoplanets, known as the radial velocity method. The radial velocity method works by observing changes in the light spectrum of a star. When a star moves slightly toward Earth, its light shifts toward the blue end of the spectrum. When it moves away, the light shifts toward the red end. By carefully measuring these shifts over time, scientists can infer the presence of an orbiting planet. This technique does not show the planet directly, but it reveals its gravitational influence. It was one of the first successful tools that allowed astronomers to confirm that planets exist beyond our solar system. The breakthrough moment in exoplanet science came in the 1990s, when the first confirmed detection of a planet orbiting a Sun-like star was announced. This discovery changed everything. It proved that planets are not unique to our solar system and that other stars can host their own planetary systems. Since that moment, the search for exoplanets has expanded rapidly, with thousands of new worlds discovered across the galaxy. Each discovery has added a new piece to the puzzle of how planetary systems form and evolve. Another major method used in exoplanet detection is the transit method. This technique relies on observing the slight dimming of a star when a planet passes in front of it. When a planet transits its star, it blocks a small portion of the starlight, causing a temporary and periodic decrease in brightness. By measuring these dips in brightness, scientists can determine the size of the planet, its orbital period, and sometimes even details about its atmosphere. This method has become one of the most productive ways of discovering exoplanets, especially with space telescopes designed for continuous observation of distant stars. The transit method has revealed that planetary systems are far more diverse than previously imagined. Before exoplanet discoveries, scientists largely assumed that our solar system was a typical example of how planets form and behave. However, the data collected from other star systems showed a very different reality. Many planetary systems look nothing like ours. Instead of small rocky planets close to their star and large gas giants farther away, astronomers found systems with giant planets orbiting extremely close to their stars, planets with highly eccentric orbits, and systems with multiple planets packed into tight configurations. One of the first surprising discoveries was the existence of hot Jupiters. These are gas giant planets similar in size to Jupiter, but orbiting extremely close to their host stars, sometimes completing an orbit in just a few days. According to traditional models of planetary formation, such planets should not exist in these positions. Gas giants are expected to form in the colder outer regions of a system where volatile compounds can condense. The presence of hot Jupiters forced scientists to rethink how planets migrate and evolve over time. It suggested that planetary systems are dynamic and can change significantly after formation. As the catalogue of exoplanets grew, scientists began to see patterns in their diversity. One of the most common types of planets discovered are super-Earths and mini-Neptunes. These are planets that are larger than Earth but smaller than Neptune. They do not exist in our solar system, yet they appear to be extremely common throughout the galaxy. Super-Earths may be rocky like Earth, or they may have thick gaseous atmospheres depending on their composition. Mini-Neptunes, on the other hand, are likely to have thick hydrogen and helium atmospheres surrounding icy or rocky cores. The abundance of these intermediate-sized planets suggests that planetary formation processes naturally produce a wide range of outcomes. It also raises important questions about habitability. Some super-Earths might have conditions suitable for life, while others might be too hot, too cold, or covered in thick atmospheres that make surface conditions extremely hostile. Understanding these planets is crucial for determining how common Earth-like environments might be in the universe. One of the most exciting aspects of exoplanet research is the search for planets located in the habitable zone of their stars. This is the region where temperatures allow liquid water to exist on a planet's surface, assuming the right atmospheric conditions. Liquid water is considered a key ingredient for life as we know it, making these planets prime candidates in the search for extraterrestrial biology. However, being in the habitable zone does not guarantee habitability. Many other factors, such as atmospheric composition, magnetic fields, and geological activity, play important roles in determining whether a planet can support life. As detection techniques improved, scientists began identifying Earth-sized planets in the habitable zones of distant stars. These discoveries sparked enormous interest because they represent some of the closest analogues to our own planet found so far. However, even with these promising candidates, there is still no direct evidence of life beyond Earth. The challenge lies not only in finding these planets, but also in analyzing their atmospheres and surface conditions in enough detail to determine whether life could exist there. Beyond rocky planets, astronomers have also discovered ocean worlds, planets that may be completely covered by deep global oceans. These worlds are unlike anything in our solar system. Instead of continents and land masses, they may consist of vast layers of water covering the entire planet. Beneath these oceans could be rocky cores or high-pressure ice layers. If such planets exist, they could potentially provide environments where life might develop in ways very different from Earth. The idea of entire planets covered in water expands the range of possible habitats in the universe significantly. At the other extreme, some exoplanets exist in environments of intense heat or cold. Lava worlds are planets so close to their stars that their surfaces are likely molten, with oceans of lava flowing across their surfaces. On the opposite end are frozen giants, planets located far from their stars or in environments where heat is minimal, causing their surfaces and atmospheres to freeze. These extreme worlds demonstrate the incredible range of planetary conditions that exist in the galaxy. Another fascinating category of exoplanets is rogue planets. These are planets that do not orbit any star. Instead, they drift through interstellar space, unbound and isolated. Rogue planets may have been ejected from their original star systems due to gravitational interactions, or may have formed independently in isolation. Without a star to provide heat and light, these planets are extremely cold and dark. However, some theories suggest that internal heat from radioactive decay or subsurface oceans might allow for limited environments where life could potentially exist even in the absence of starlight. As technology continues to improve, scientists are now able to study not only the existence of exoplanets, but also their atmospheres. By analyzing the light that passes through a planet's atmosphere during a transit, researchers can detect the presence of gases such as water vapor, carbon dioxide, methane, and other chemical compounds. These atmospheric signatures provide clues about the composition, climate, and potential habitability of distant worlds. In some cases, they may even reveal signs that could indicate biological activity. The study of exoplanets has fundamentally changed our understanding of the universe. It has revealed that planets are not rare exceptions, but common features of star systems. It has shown that planetary systems are diverse, dynamic, and often very different from our own. Most importantly, it has expanded the possibilities for where life might exist beyond Earth. As we move deeper into the exploration of exoplanets, the next step is to understand their diversity in more detail. From gas giants trapped in close orbits to Earth, like worlds in distant habitable zones, from ocean-covered planets to rogue wanderers in interstellar space, each category of exoplanet tells a different story about how planets form and evolve. This diversity is not just a scientific curiosity, but a key to understanding our place in the universe. The journey beyond our solar system has only just begun, and each new discovery brings us closer to answering one of the oldest questions in human history. Are we alone, or is the universe filled with countless worlds waiting to be explored? The discovery of exoplanets did not happen all at once, nor did it begin with clear evidence pointing directly to other worlds. Instead, it was a slow and careful process built on decades of indirect reasoning, technological improvement, and scientific persistence. For most of human history, planets beyond our solar system were purely hypothetical. The stars were visible, but their companions remained hidden. It was only through the refinement of observational techniques and the development of precise instruments that humanity finally began to uncover the first real evidence that planets exist beyond our own solar system. Before the first confirmed detections, astronomers already suspected that other planetary systems should exist. The reasoning was based on logic and probability. The Sun is just one star among billions in the Milky Way galaxy, and it seemed unlikely that it would be the only one with planets. However, without direct evidence, this remained an assumption. The challenge was not in believing that exoplanets could exist, but in finding a way to observe them. Early attempts to detect exoplanets focused on understanding how a planet might influence its star. Even if a planet could not be seen directly, its presence might still be inferred through its gravitational effects. A star with a planet does not remain perfectly stationary. Instead, both the star and the planet orbit a shared center of mass. This causes the star to move in a very small orbit or wobble. Detecting this wobble became one of the first promising methods for identifying exoplanets. This method is known as radial velocity detection. It relies on the fact that when a star moves slightly toward or away from Earth, the light it emits shifts in wavelength. When the star moves toward us, its light shifts toward the blue end of the spectrum. When it moves away, the light shifts toward the red end. This phenomenon is called the Doppler effect. By carefully measuring these tiny shifts in the star's light over time, astronomers can detect the presence of an orbiting planet. Although the concept is simple in principle, the practical application is extremely difficult. The movement of a star caused by a planet is incredibly small. For example, Jupiter causes the Sun to move by only a very slight amount relative to its size. Detecting such a subtle motion requires extremely precise instruments, capable of measuring changes in light at the level of meters per second or even less. For many years, this level of precision was not achievable. Despite these challenges, astronomers continued refining their instruments and techniques. The development of more sensitive spectrographs allowed scientists to measure stellar light with unprecedented accuracy. By the late 20th century, technology had advanced enough that radial velocity measurements could finally begin to reveal the presence of planets around other stars. The breakthrough came in 1992, when the first confirmed detection of planets outside our solar system was announced. These planets were not orbiting a sun-like star, but rather a pulsar, a highly magnetized and rapidly rotating neutron star. While this discovery was groundbreaking, it was also unusual because pulsar planets are formed under extreme and unusual conditions, likely after a supernova explosion. However, the real milestone came a few years later. In 1995, astronomers announced the discovery of a planet orbiting a sun-like star called 51 Pegasi. This planet, later named 51 Pegasi b, was a hot Jupiter, a gas giant orbiting extremely close to its star. Its discovery shocked the scientific community, because it did not fit existing models of planetary formation. According to traditional theories, gas giants should form far from their stars, where temperatures are low enough for volatile compounds to condense. Finding such a massive planet so close to its star forced scientists to reconsider how planetary systems evolve. The discovery of 51 Pegasi b marked the beginning of the modern era of exoplanet science. From that point onward, the number of known exoplanets began to grow rapidly. Each new discovery added to a growing catalogue of planetary diversity that was far greater than anyone had anticipated. Planets were found in a wide range of sizes, temperatures, and orbital configurations, revealing that planetary systems are far more varied than the relatively orderly structure of our own solar system. One of the most important developments that followed was the refinement of detection methods. While radial velocity provided the first confirmed discoveries, another method soon became equally important. This method is known as the transit method. Instead of measuring the motion of a star, it focuses on the slight dimming of a star's light when a planet passes in front of it. When a planet transits its star, it blocks a small fraction of the star's light. This causes a temporary and periodic decrease in brightness. By observing these dips in brightness over time, astronomers can determine the size of the planet, its orbital period, and sometimes even details about its atmosphere. The transit method has the advantage of being able to detect many planets at once if a large number of stars are observed simultaneously. The development of space-based telescopes greatly enhanced the effectiveness of the transit method. Instruments such as the Kepler Space Telescope were designed specifically to monitor thousands of stars continuously, searching for the subtle signatures of transiting planets. Kepler revolutionized exoplanet science by discovering thousands of new worlds, dramatically expanding the known population of planets in the galaxy. With the data collected from Kepler and other missions, scientists began to recognize patterns in planetary populations. One of the most surprising findings was that planets are extremely common. It appears that most stars in the galaxy host at least one planet, and many have multiple. This means that planetary systems are not rare exceptions, but rather the norm in the universe. Another major discovery was the existence of planets that do not resemble anything in our solar system. Hot Jupiters, super-Earths, and mini-Neptunes all challenged existing models of planetary formation. Hot Jupiters, as mentioned earlier, orbit very close to their stars, often completing an orbit in just a few days. Super-Earths are rocky planets, larger than Earth but smaller than Neptune, while mini-Neptunes are smaller versions of gas giants with thick atmospheres. The discovery of these planets forced scientists to rethink how planets form and migrate. It became clear that planetary systems are dynamic and can change significantly after their initial formation. Planets can move inward or outward from their original positions due to gravitational interactions with other planets or with the protoplanetary disk from which they formed. One of the most important implications of these discoveries is that our solar system may not be typical. For a long time, scientists assumed that the arrangement of planets in our system, with small rocky planets near the Sun and large gas giants farther out, was a standard pattern. However, Exoplanet discoveries have shown that this configuration may actually be relatively uncommon. Instead, many systems appear to be much more chaotic or compact. This realization has profound implications for the search for life beyond Earth. If planetary systems are so diverse, then the conditions for habitability may also be more varied than previously thought. Planets that are very different from Earth might still have environments capable of supporting life under the right conditions. This greatly expands the number of potential habitats in the galaxy. As detection techniques improved further, scientists began to focus not only on finding planets, but also on characterizing them. This includes studying their sizes, masses, densities, and orbital properties. By combining data from both radial velocity and transit methods, it is possible to determine both the mass and radius of a planet. This allows scientists to calculate its density, which in turn provides clues about its composition. For example, a dense planet is likely to be rocky, while a less dense one may be composed mostly of gas or ice. One of the most exciting frontiers in exoplanet science is the study of atmospheres. When a planet transits its star, a small portion of the starlight passes through the planet's atmosphere before reaching Earth. By analyzing this light, scientists can identify the chemical composition of the atmosphere. This technique has already revealed the presence of molecules such as water vapor, carbon dioxide, methane, and sodium in the atmospheres of distant planets. The ability to study exoplanet atmospheres opens the possibility of detecting biosignatures, chemical indicators that could suggest the presence of life. For example, the simultaneous presence of oxygen and methane in an atmosphere could indicate biological processes. Since these gases tend to react with each other and would not remain stable together for long periods without continuous replenishment. While no definitive biosignatures have been confirmed yet, this remains one of the most important goals in modern astronomy. The discovery revolution has transformed our understanding of the universe in a fundamental way. What was once a single known planetary system has become a galaxy filled with diverse and complex worlds. Each new exoplanet adds to the growing realization that planets are not rare or special, but common components of the cosmos. As we move deeper into the study of exoplanets, the focus shifts from simply finding them to understanding their nature in detail. The next stage involves exploring the wide variety of planetary types that exist, from massive gas giants to small rocky worlds, from scorched lava planets to frozen ice worlds, and from stable Earth-like environments to chaotic and extreme systems. Each category reveals something new about the processes that shape planetary systems and the possibilities for life beyond Earth. Among the many surprising discoveries in exoplanet science, few have challenged scientific expectations more than the existence of hot Jupiters. These are giant gas planets, often similar in size or even larger than Jupiter, yet orbiting extremely close to their host stars. In some cases, they complete a full orbit in just a few Earth days. Their discovery fundamentally changed how scientists think about planetary systems, forcing a complete revision of earlier models of planet formation and migration. Before hot Jupiters were discovered, astronomers largely based their theories of planetary formation on observations of our own solar system. In this model, Gas giants like Jupiter and Saturn form in the colder outer regions of a planetary system. This is because the building blocks of gas giants, such as hydrogen compounds, water and methane, can only condense into solid or icy materials at low temperatures. These solid cores then accumulate large gaseous atmospheres over time. According to this understanding, gas giants should remain far from their stars while rocky planets form closer in. However, the discovery of hot Jupiters completely contradicted this expectation. Instead of finding gas giants far from their stars, astronomers found them orbiting at distances much closer than Mercury orbits the Sunday. Some of these planets are so close to their stars that their surface temperatures reach thousands of degrees. At such extreme temperatures, even metals can exist in vaporized form in their atmospheres. These planets are not only massive and gaseous, but also subjected to intense stellar radiation and gravitational forces. One of the first hot Jupiters discovered, 51 Pegasi b, orbiting the star, 51 Pegasi, stunned the scientific community. It was roughly half the mass of Jupiter, but orbited its star in just 4 days. This was completely unlike anything seen in our solar system. Its existence suggested that either planetary formation was far more flexible than previously thought, or that planets could migrate dramatically from their original positions. The idea of planetary migration quickly became a central concept in explaining hot Jupiters. According to this theory, gas giants do not necessarily form where we see them today. Instead, they may form in the outer regions of a planetary system and then gradually move inward over time. This movement can be caused by interactions with the protoplanetary disk, gravitational interactions with other planets, or even complex orbital resonances. As a result, a planet that forms far from its star can eventually spiral inward to a very close orbit. This process of migration is not simple or uniform. It depends on many factors, including the mass of the planet, the density of the surrounding disk, and the presence of other planetary bodies. In some cases, migration may occur relatively smoothly, with the planet gradually moving inward over millions of years. In other cases, it may be chaotic, involving gravitational interactions that scatter planets into highly eccentric orbits before they settle into stable configurations. Hot Jupiters are particularly important because they are relatively easy to detect compared to smaller planets. Their large size and close proximity to their stars produce strong signals in both the radial velocity and transit methods. When a hot Jupiter transits its star, it blocks a significant portion of the star's light, making the dip in brightness more noticeable. Similarly, their gravitational influence on their host stars is strong enough to produce measurable Doppler shifts. Despite being easier to detect, hot Jupiters are still relatively rare compared to smaller exoplanets. However, their discovery early in the history of exoplanet science created a selection bias. At first, astronomers thought they might be the most common type of planet simply because they were the easiest to find. As detection techniques improved, it became clear that smaller planets, such as super-Earths and mini-Neptunes, are actually far more common. Hot Jupiters are just one part of a much broader and more diverse planetary population. One of the most fascinating aspects of hot Jupiters is their extreme environments. Because they orbit so close to their stars, they are exposed to intense radiation and tidal forces. Their atmospheres are often heated to thousands of degrees, causing chemical elements to behave in unusual ways. Some hot Jupiters are thought to have atmospheres where clouds are made of vaporized metals such as iron or titanium. Others may have strong atmospheric winds that circulate heat from the star-facing side to the dark side of the planet. In many cases, hot Jupiters are tidally locked, meaning the same side of the planet always faces the star, just like the Moon always shows the same face to Earth. This creates extreme temperature differences between the day side and the night side. The day side can be scorching hot, while the night side may be significantly cooler. This temperature contrast drives powerful atmospheric circulation patterns, with winds that can reach speeds of thousands of kilometers per hour. These extreme conditions make hot Jupiters some of the most dynamic and violent planetary environments known. They are not stable, Earth-like worlds, but rather highly energetic systems shaped by constant interaction with their stars. Studying them provides valuable insight into how planets behave under extreme conditions and how planetary atmospheres respond to intense external forces. The existence of hot Jupiters also has important implications for the formation and stability of other planets in the same system. If a gas giant migrates inward, it can disrupt the orbits of smaller planets, potentially ejecting them from the system or altering their trajectories. This means that systems with hot Jupiters may have very different architectures compared to systems like our own. In some cases, the migration of a giant planet may prevent the formation of Earth-like planets in stable orbits. However, not all systems with hot Jupiters are necessarily devoid of other planets. Some observations suggest that smaller planets can exist in the same system, either in outer orbits or in stable resonant configurations. This indicates that planetary systems are highly adaptable and can evolve into a wide variety of stable arrangements even after significant dynamical changes. Another important aspect of hot Jupiters is their interaction with their host stars. Because they are so close, they can have measurable effects on stellar activity. In some cases, magnetic interactions between the planet and the star may enhance stellar flares or influence the star's magnetic field. This creates a complex relationship between the planet and its star that goes beyond simple orbital motion. Over time, hot Jupiters may also experience atmospheric loss due to intense stellar radiation. The heat from the star can cause the upper layers of the planet's atmosphere to escape into space, forming long tails of gas that trail behind the planet. In extreme cases, this process can significantly reduce the mass of the planet over billions of years, potentially transforming it into a smaller and less massive object. The study of hot Jupiters has also helped scientists refine models of planetary atmospheres. By observing how light filters through their atmospheres during transits, researchers can identify chemical signatures and temperature profiles. These observations have revealed unexpected chemical compositions and dynamic weather systems that challenge simple models of planetary atmospheres. Despite their extreme nature, hot Jupiters have become key objects of study in exoplanet science. They serve as natural laboratories for understanding planetary physics under conditions far more extreme than anything found in our solar system. Their discovery marked the beginning of a broader realization that planetary systems are far more diverse and dynamic than previously believed. As more exoplanets were discovered, it became clear that hot Jupiters are just one part of a much larger spectrum of planetary types. From massive gas giants orbiting close to their stars to small rocky planets in distant habitable zones, the diversity of exoplanets continues to expand our understanding of what is possible in planetary systems. The next step in this exploration involves looking beyond hot Jupiters to other unusual types of planets, such as super-Earths and mini-Neptunes, which appear to be among the most common planets in the galaxy. These worlds further challenge our assumptions and reveal just how varied planetary systems can be. As exoplanet discoveries continued to expand, astronomers began to notice that the most common types of planets in the galaxy do not resemble anything found in our own solar system. Among the most frequently detected worlds are super-Earths and mini-Neptunes, two categories of planets that sit between the size of Earth and Neptune. These planets have no direct analogue in our solar system, yet they appear to be widespread across the Milky Way. Their existence has forced scientists to rethink the very definition of what a planet can be and how planetary systems naturally form. A super-Earth is generally defined as a planet with a mass larger than Earth but significantly smaller than that of Neptune. This range is broad, and it includes planets that may be rocky, like Earth, or partially gaseous, depending on their composition and atmospheric conditions. Despite the name, a super-Earth is not necessarily Earth-like in terms of habitability. The term only refers to size and mass, not surface conditions or environmental similarity. Some super-Earths may have thick atmospheres, extreme temperatures, or entirely different chemical compositions compared to Earth. Mini-Neptunes, on the other hand, are smaller versions of Neptune or Uranus. These planets typically have thick hydrogen and helium atmospheres surrounding icy or rocky cores. Unlike super-Earths, mini-Neptunes are generally not considered rocky worlds with solid surfaces. Instead, they are thought to be gas-rich or volatile-rich planets with deep atmospheres that may extend far below their cloud layers. In many cases, the exact boundary between a super-Earth and a mini-Neptune is not clearly defined, and some planets may fall somewhere in between these two categories. One of the most surprising discoveries in exoplanet science is that planets in the size range between Earth and Neptune are extremely common in the galaxy, even though they do not exist in our solar system. This was completely unexpected. Before exoplanet surveys, scientists assumed that planetary systems would resemble our own, with small rocky planets near the star and large gas giants farther out. However, data from missions like Kepler revealed that the most common planets are actually those in this intermediate size range. This discovery has had a major impact on theories of planetary formation. It suggests that the processes that build planets naturally favor the creation of super-Earths and mini-Neptunes. In other words, the architecture of our solar system may be somewhat unusual rather than typical. This realization has forced scientists to reconsider how planetary systems evolve from their initial formation in protoplanetary disks. Planet formation begins in a disk of gas and dust surrounding a young star. Within this disk, small particles collide and stick together, gradually forming larger bodies known as planetesimals. Over time, these planetesimals grow into protoplanets through repeated collisions and gravitational interactions. Depending on their location in the disk and the available material, these protoplanets can evolve into rocky planets, gas giants, or intermediate types such as super-Earths and mini-Neptunes. One of the key factors influencing the final outcome is the availability of gas in the protoplanetary disk. If a growing planet reaches a critical mass while gas is still present, it can begin to accumulate a thick atmosphere, potentially becoming a mini-Neptune. If gas dissipates before the planet grows large enough, it may remain a rocky super-Earth. This delicate balance between timing and mass accumulation helps explain the wide variety of planets observed in exoplanet systems. Another important factor is planetary migration. As discussed in the previous chapter, planets do not always remain in the same position where they form. Interactions with the gas disk or with other planets can cause them to move inward or outward. This migration can significantly alter a planet's final composition and orbit. For example, a planet that forms in the outer regions of a system may migrate inward and lose some of its atmosphere due to stellar radiation, transforming it from a mini-Neptune into a super-Earth. The boundary between super-Earths and mini-Neptunes is not always clear, and this ambiguity reflects the complexity of planetary evolution. Some planets may have thin hydrogen atmospheres over rocky surfaces, while others may have deep gaseous envelopes surrounding icy or metallic cores. The diversity of these worlds makes it difficult to classify them into strict categories, and ongoing research continues to refine our understanding of their properties. One of the most intriguing questions about super-Earths is whether any of them could be habitable. Because they are larger than Earth, they may have stronger gravity, which can influence their atmospheres and surface conditions. A stronger gravitational field could help a planet retain a thick atmosphere, potentially creating stable climates. However, it could also lead to extreme pressure conditions on the surface, making them inhospitable to life as we know it. Some super-Earths are located in the habitable zones of their stars, where temperatures might allow liquid water to exist. These planets are of particular interest because they represent potential environments where life could emerge. However, being in the habitable zone does not guarantee habitability. Many other factors must be considered, including atmospheric composition, volcanic activity, magnetic fields, and geological stability. Mini-Neptunes, on the other hand, are generally considered less likely to support life on their surfaces if they have surfaces at all. Their thick atmospheres and high-pressure environments make it difficult for conditions similar to Earth to exist. However, some theories suggest that moons orbiting mini-Neptunes, or layers within their atmospheres, could potentially harbor environments where life might exist under very different conditions than those on Earth. The discovery of these planets has also expanded our understanding of atmospheric science. Super-Earths and mini-Neptunes often have complex atmospheres that differ significantly from those of Earth or the gas giants in our solar system. By studying the light that passes through these atmospheres during transits, scientists can detect the presence of various gases and compounds. These observations provide clues about the chemical processes occurring on these distant worlds. For example, some mini-Neptunes have been found to contain large amounts of hydrogen and helium, similar to gas giants, while others show signs of heavier molecules such as water vapor or methane. Super-Earths may have atmospheres rich in carbon dioxide, nitrogen, or other gases, depending on their formation history and geological activity. These differences highlight the wide range of atmospheric conditions that can exist on planets of similar size. Temperature also plays a crucial role in shaping the characteristics of these planets. Super-Earths located close to their stars may have extremely high surface temperatures, potentially leading to molten surfaces or volcanic activity. In contrast, those located farther away may be cold and frozen. Mini-Neptunes may experience intense atmospheric heating in their upper layers, leading to dynamic weather systems and high-altitude cloud formation. Another important aspect of these planets is their potential internal structure. Super-Earths may have large rocky or metallic cores, possibly surrounded by thin atmospheres. Some may even have active geology, including plate tectonics and volcanic activity, which could influence their surface conditions and atmospheric composition. Mini-Neptunes, in contrast, may have deep layers of gas surrounding icy or rocky interiors with extreme pressure conditions at lower depths. The diversity of super-Earths and mini-Neptunes suggests that planetary formation is a highly flexible process. Small changes in initial conditions can lead to very different outcomes. This flexibility explains why the galaxy contains such a wide variety of planets, many of which do not resemble anything in our own solar system. As observational technology continues to improve, scientists are beginning to characterize these planets in greater detail. Future telescopes will be able to analyze their atmospheres with higher precision, measure their temperatures more accurately, and potentially identify signs of chemical disequilibrium that could indicate biological activity. These advancements will help determine whether any of these planets could support life. The study of super-Earths and mini-Neptunes also plays a crucial role in understanding the potential abundance of habitable worlds in the galaxy. If even a small fraction of super-Earths are capable of supporting life, then the number of potentially habitable planets in the universe could be far greater than previously estimated. This has profound implications for the search for extraterrestrial life. In many ways, these planets represent a bridge between the familiar and the unknown. They are larger than Earth, yet smaller than the gas giants. They may be rocky or gaseous, hot or cold, stable or dynamic. Their diversity reflects the complexity of planetary formation and the wide range of conditions that exist in the universe. As we continue to explore exoplanets, super-Earths and mini-Neptunes will remain central to our understanding of planetary systems. They challenge our assumptions, expand our definitions, and reveal that the universe is far more diverse than we ever imagined. The next step in this journey takes us toward even more extreme and varied worlds, including planets that may be entirely covered in oceans or composed of exotic materials under conditions unlike anything found in our solar system. Among the most intriguing categories of exoplanets are those that exist in regions where conditions might allow liquid water to persist on their surfaces. These are known as Earth-like worlds in the habitable zone, often described as being located in the Goldilocks zone of their stars, where temperatures are neither too hot nor too cold for liquid water to exist under the right atmospheric conditions. These planets represent some of the most important targets in the search for life beyond Earth, because water is considered a fundamental ingredient for life as we understand it. The concept of the habitable zone is based on a relatively simple idea. A planet's distance from its star determines how much energy it receives. If a planet is too close, its surface becomes too hot, causing water to evaporate and potentially escape into space. If it is too far, the surface becomes too cold and water freezes into ice. The habitable zone is the region around a star where temperatures might allow liquid water to exist on a planet's surface, assuming the planet has a suitable atmosphere to regulate temperature. However, the habitable zone is not a fixed or simple boundary. It depends on many factors, including the type and brightness of the star, the composition of the planet's atmosphere, and the planet's internal heat sources. For example, a planet with a thick greenhouse gas atmosphere might retain heat more effectively and remain warm even if it is located farther from its star. Conversely, a planet with a thin atmosphere might struggle to maintain liquid water even if it is located within the traditional habitable zone. The discovery of exoplanets in habitable zones has been one of the most exciting developments in modern astronomy. These planets are often referred to as potentially habitable because they meet some of the basic conditions thought to be necessary for life. However, it is important to emphasize that being in the habitable zone does not guarantee habitability. It simply means that the temperature conditions might allow for liquid water under the right circumstances. One of the earliest and most significant discoveries in this category was the identification of planets orbiting within the habitable zones of their stars using data from space telescopes like Kepler. These discoveries revealed that Earth-sized planets in potentially habitable regions are not rare. In fact, they appear to be relatively common in the galaxy. This finding greatly expanded the number of worlds that could potentially support life. Earth-like exoplanets vary widely in their characteristics. Some are similar in size and composition to Earth, with rocky surfaces and thin atmospheres. Others are larger super-Earths that may have stronger gravity and thicker atmospheres. Some orbit small red dwarf stars, while others orbit sun-like stars similar to our own Sunday. Each of these factors plays a critical role in determining whether a planet could support life. One of the most important considerations for habitability is the type of star a planet orbits. Red dwarf stars are the most common type of star in the galaxy, and many habitable zone exoplanets have been found orbiting them. However, red dwarf stars are also known for their variability and frequent stellar flares. These flares can release large amounts of radiation, which may strip away a planet's atmosphere or make surface conditions hostile to life. On the other hand, red dwarf stars have extremely long lifespans, potentially lasting trillions of years, which could provide long, stable periods for life to develop under the right conditions. Sun-like stars offer a different set of conditions. Their habitable zones are located farther from the star compared to red dwarfs, which may reduce the risk of tidal locking a situation where one side of the planet always faces the star. Tidal locking can create extreme temperature differences between the day side and night side of a planet. However, even tidally locked planets may still be habitable if they have thick enough atmospheres or oceans capable of distributing heat. Atmospheric composition is another critical factor in determining habitability. Earth's atmosphere plays a vital role in maintaining surface conditions suitable for life. It regulates temperature through the greenhouse effect, protects the surface from harmful radiation, and provides essential gases for biological processes. Exoplanets with similar atmospheric compositions could potentially have stable environments where liquid water can persist. Scientists study exoplanet atmospheres using a technique known as transmission spectroscopy. When a planet transits its star, some of the starlight passes through the planet's atmosphere before reaching observers on Earth. Different gases absorb different wavelengths of light, creating unique spectral signatures. By analyzing these signatures, scientists can identify the presence of gases such as water vapor, carbon dioxide, methane, and oxygen. These gases can provide important clues about the planet's environment and potential habitability. The detection of water vapor in an exoplanet's atmosphere is particularly significant. Water is considered essential for life as we know it because it serves as a solvent for chemical reactions and plays a central role in biological processes. However, the presence of water vapor alone does not confirm habitability. It must be considered alongside other factors such as temperature, atmospheric pressure, and chemical balance. Another important aspect of habitable zone planets is their geological activity. On Earth, processes such as plate tectonics and volcanism play a crucial role in regulating the planet's climate and recycling essential elements. Plate tectonics helps maintain long-term climate stability by controlling carbon dioxide levels through the carbon silicate cycle. Volcanic activity releases gases into the atmosphere, which can help maintain pressure and temperature balance. Exoplanets with similar geological activity may have more stable and long-lasting habitable environments. Magnetic fields are also important for habitability. A planet's magnetic field protects its atmosphere from being stripped away by stellar wind, a stream of charged particles emitted by stars. Without a strong magnetic field, a planet may gradually lose its atmosphere over time, making it less capable of supporting life. Earth's magnetic field is generated by the movement of molten iron in its core, and similar processes may exist on other rocky planets. Despite the promising conditions found on some habitable zone exoplanets, there are still many uncertainties. One of the biggest challenges is that we currently cannot directly observe the surfaces of most exoplanets. Instead, we rely on indirect measurements and models to infer their properties. This means that our understanding of these worlds is still limited, and many assumptions must be made based on incomplete data. Even so, the discovery of potentially habitable planets has had a profound impact on science and philosophy. It suggests that Earth may not be unique in its ability to support life. If habitable environments are common in the galaxy, then the possibility that life exists elsewhere becomes much more plausible. This has led to one of the most important questions in modern science. Are we alone in the universe? Some of the most promising candidates for habitable exoplanets are located relatively close to Earth in astronomical terms. These include planets orbiting nearby red dwarf stars that lie within a few dozen light-years of our solar system. While still extremely distant by human standards, these planets are close enough that future technological advancements might one day allow for more detailed observation or even interstellar exploration. However, even among these promising candidates, conditions can vary widely. Some planets may have thick atmospheres that trap too much heat, creating runaway greenhouse effects similar to Venus. Others may be too cold, with frozen surfaces and limited atmospheric circulation. Some may experience extreme radiation from their host stars, while others may be more stable and calm. The diversity of habitable zone exoplanets reflects the complexity of planetary systems. There is no single recipe for habitability. Instead, it appears that a wide range of conditions may potentially support life, depending on how various factors interact. This flexibility greatly increases the number of worlds that could potentially harbor life, even if their conditions differ significantly from those on Earth. As observational technology continues to advance, future telescopes will be able to study these planets in much greater detail. Instruments designed to directly image exoplanets, analyze their atmospheres, and detect chemical signatures will play a key role in identifying the most promising candidates for life. These advancements may eventually allow scientists to move beyond detection and toward detailed characterization of Earth-like worlds. The search for habitable zone planets is not just about finding places that resemble Earth. It is about understanding the full range of environments in which life might exist. Life on Earth is adapted to a specific set of conditions, but the universe may contain many other environments where life could emerge in different forms. By studying these planets, scientists hope to expand the definition of habitability and explore the possibility that life may be more diverse than previously imagined. As we continue to explore these distant worlds, the next step is to look beyond simple habitability and consider even more exotic environments. Some planets are not just Earth-like, but radically different, such as ocean worlds covered entirely by deep global seas, or planets with extreme conditions that challenge our understanding of physics and chemistry. These worlds further expand the boundaries of what is possible in planetary science and bring us closer to understanding the true diversity of the universe. As the catalogue of exoplanets has grown, one of the most surprising revelations is that many worlds in the universe may not resemble Earth at all. Even if they are located in regions where temperatures could allow liquid water instead of rocky continents, mountains, and dry land, some planets may be entirely covered by deep global oceans. These are known as ocean worlds, and they represent a radically different type of planetary environment, one that challenges our assumptions about what a habitable planet should look like. The concept of an ocean world emerges naturally from the diversity of planetary formation. During the early stages of a planetary system, water is one of the most abundant volatile compounds. It can exist as ice in the outer regions of a protoplanetary disk and as vapor or liquid in warmer regions. As planets form and migrate, large amounts of water can become trapped in their interiors or accumulate on their surfaces. Under the right conditions, a planet may end up with so much water that it completely submerges any rocky surface beneath a global ocean. In such a world, there would be no continents, no dry land, and possibly no exposed rock at all. Instead, the entire surface would be a vast, uninterrupted ocean stretching around the planet. The depth of these oceans could vary significantly, but in many theoretical models they could be tens or even hundreds of kilometers deep. Beneath this liquid layer, there may be high-pressure ice phases or rocky mantles that never interact directly with the atmosphere. Ocean worlds are fundamentally different from Earth in terms of structure and environment. On Earth, life has access to both land and sea, with complex interactions between atmosphere, oceans, and continents. These interactions play a crucial role in regulating climate and supporting diverse ecosystems. On an ocean world, however, the absence of land eliminates many of these processes. The entire planetary surface becomes a continuous fluid environment with energy and nutrients distributed in very different ways. One of the key questions about ocean worlds is whether they can support life. On Earth, life is believed to have originated in water, making oceans a natural environment for biological processes. In principle, an ocean world could provide a stable and long-lasting environment for life to develop. However, the lack of land and geological diversity could limit the availability of certain chemical elements that are important for complex life. On Earth, continents play an important role in recycling nutrients through erosion, volcanic activity, and tectonic processes. These processes help maintain a dynamic balance of elements such as carbon, nitrogen, and phosphorus. In a deep global ocean with no exposed land, these recycling mechanisms may be absent or significantly reduced. This raises questions about how nutrient cycles would operate in such environments. One possibility is that hydrothermal vents at the bottom of ocean worlds could provide a source of energy and nutrients. On Earth, hydrothermal vents are found along mid-ocean ridges, where geothermal energy heats water and releases chemically rich fluids into the surrounding ocean. These environments host unique ecosystems that do not rely on sunlight, but instead on chemical energy. If similar processes exist on ocean worlds, they could potentially support life in deep subsurface environments. Another important factor is the thickness and composition of the ocean itself. In some models, ocean worlds may have extremely deep layers of water under high pressure. At great depths, water can transition into exotic high-pressure phases of ice that behave differently from ordinary ice. These layers could separate the liquid ocean from the rocky core of the planet, potentially limiting the exchange of materials between the interior and the ocean above. The presence of such high-pressure ice layers raises important questions about habitability. If the ocean is isolated from the rocky core, it may lack access to essential minerals and chemical compounds that are typically supplied by geological activity. This could make it more difficult for life to develop or sustain itself over long periods. However, if there are mechanisms that allow for mixing or energy transfer between layers, then habitability may still be possible. The atmosphere of ocean worlds also plays a crucial role in determining their conditions. Some ocean worlds may have thick atmospheres, rich in water vapor, carbon dioxide, or other gases. These atmospheres could help regulate temperature and maintain stable surface conditions. However, if the atmosphere is too thick, it could create high-pressure environments that significantly alter the behavior of the ocean surface. Climate on ocean worlds would likely be very different from Earth's climate. Without continents to influence weather patterns, ocean circulation would dominate the global climate system. Large-scale currents could distribute heat around the planet, potentially creating relatively uniform temperature conditions across the surface. However, the absence of land could also mean fewer stable environmental niches, which might affect the development of complex ecosystems. One of the most intriguing aspects of ocean worlds is the possibility of entirely different forms of life. If life exists in these environments, it would have evolved under very different conditions from those on Earth. Without land, there would be no terrestrial ecosystems. Instead, all life would be aquatic, potentially adapted to deep ocean pressures, limited light conditions, and unique chemical environments. On Earth, life in the deep ocean already demonstrates remarkable adaptations. Organisms living near hydrothermal vents or in the deepest parts of the ocean can survive extreme pressure, darkness, and chemical conditions. These examples suggest that life can thrive in environments very different from surface conditions. Ocean worlds could extend these possibilities even further, potentially hosting ecosystems that are completely independent of sunlight. Another important consideration is energy availability. On Earth, most ecosystems ultimately depend on sunlight through photosynthesis. However, in deep ocean environments where sunlight cannot penetrate, life depends on chemical energy sources. On ocean worlds, similar energy sources may exist in the form of hydrothermal activity or chemical gradients within the ocean. These energy sources could potentially support biospheres that are completely independent of stellar light. The study of ocean worlds also raises important questions about planetary formation. How do such large amounts of water accumulate on a planet? One possibility is that water-rich planets form in the outer regions of planetary systems, where ice is abundant, and then migrate inward. Another possibility is that water is delivered during the late stages of planetary formation through impacts from comets and icy bodies. In either case, the final result is a planet with a very high water content relative to its mass. Some ocean worlds may also exist in subsurface forms, where liquid water is hidden beneath thick layers of ice. These ice-covered oceans are of particular interest because they may provide stable environments protected from harsh surface conditions. In our own solar system, moons such as Europa and Enceladus are believed to have subsurface oceans beneath their icy crusts. Similar worlds may exist around other stars, expanding the range of potentially habitable environments. The detection of ocean worlds is challenging because their surfaces are hidden beneath clouds or water layers. However, indirect methods such as analyzing their density, atmospheric composition, and orbital characteristics can provide clues about their nature. A planet with a relatively low density may indicate a high water content, suggesting the presence of a global ocean. Similarly, atmospheric signatures of water vapor can support the hypothesis of an ocean-rich environment. As observational technology improves, scientists hope to study these worlds in greater detail. Future telescopes may be able to analyze their atmospheres with higher precision, detect signs of chemical disequilibrium, and possibly identify biosignatures. These advancements could help determine whether ocean worlds are common habitats for life in the universe. Ocean worlds represent a major expansion of our understanding of habitability. They show that life does not necessarily require land, and that entirely aquatic environments may be capable of supporting complex biological systems. This greatly broadens the range of environments that scientists must consider in the search for extraterrestrial life. Beyond ocean worlds, the diversity of exoplanets continues to expand into even more extreme categories. Some planets are not only covered in water, but exist in conditions of extreme temperature and pressure. Others are exposed to intense stellar radiation or wander through space without any star at all. Each of these environments provides new insights into the limits of planetary formation and the possibilities for life in the universe. As we continue this journey through the vast diversity of exoplanets, we move from familiar Earth-like conditions to increasingly exotic and extreme environments, revealing a universe far more varied and complex than previously imagined. Among the most mysterious objects discovered in the galaxy are worlds that do not orbit any star at all. These are known as rogue planets, also called interstellar planets or orphan planets. Unlike the planets in our solar system, which are bound to the Sun by gravity, rogue planets drift freely through the galaxy, untethered to any stellar system. They move silently through interstellar space, dark, cold, and invisible, except under very specific observational conditions. Their existence reveals a hidden population of planets that challenge our understanding of how planetary systems form and evolve. The idea of rogue planets might seem unusual at first, because most planets we observe are clearly part of stable systems orbiting stars. However, theoretical models of planetary formation suggest that not all planets remain in the systems where they are born. During the early stages of planetary system development, gravitational interactions between forming planets can be extremely chaotic. Large planets can scatter smaller ones, and close encounters can dramatically alter orbital paths. In some cases, a planet may gain enough velocity from these interactions to escape the gravitational pull of its host star entirely. When this happens, the planet is ejected into interstellar space, becoming a rogue planet. Once free from its star, it no longer receives light or heat from a nearby stellar source. It becomes a solitary traveler in the vast darkness between stars, moving through the galaxy on an independent trajectory determined only by its initial velocity and the gravitational influence of the galaxy as a whole. Rogue planets may also form independently in space without ever being part of a star system. In these cases, they could originate from the collapse of small clouds of gas and dust that are not massive enough to ignite nuclear fusion and become stars. Instead, they form directly as planetary mass objects floating freely in space. This means that rogue planets are not necessarily former members of planetary systems, but can also be primordial objects formed in isolation. One of the most important characteristics of rogue planets is their extreme environment. Without a star, there is no external source of energy to warm their surfaces. As a result, they are typically extremely cold, with surface temperatures that may approach those of deep space itself. Any atmosphere they possess would likely be frozen or extremely thin. Their surfaces would be dark, with no visible light except for faint emissions from internal heat sources or occasional interactions with cosmic radiation. Despite these harsh conditions, rogue planets are not necessarily completely inert. Many of them may retain internal heat generated during their formation. This heat can come from radioactive decay of elements within their interiors or from residual energy left over from their formation process. In some cases, this internal heat may be sufficient to maintain subsurface oceans beneath thick layers of ice. This possibility has led to one of the most intriguing ideas in planetary science, that rogue planets could potentially harbor life in subsurface environments. Even without sunlight, liquid water could exist beneath an insulating ice layer if internal heat is sufficient. On Earth, similar environments exist in polar regions and beneath ice sheets, where microbial life has been found in extreme conditions. If similar processes occur on rogue planets, they could provide stable environments for life far from any star. The concept of subsurface oceans on rogue planets expands the traditional definition of habitability. It suggests that life does not necessarily require a star or surface light to exist. Instead, it could be sustained by internal energy sources and chemical reactions occurring beneath the surface. This greatly increases the number of potential habitats in the galaxy, since rogue planets may be extremely common. Detecting rogue planets is extremely challenging because they do not emit light and do not pass in front of stars in predictable ways. However, astronomers have developed indirect methods to identify them. One such method is gravitational microlensing. When a rogue planet passes in front of a distant star, its gravity can bend and magnify the light of that star, creating a temporary brightening effect. By analyzing these events, scientists can infer the presence of otherwise invisible planets. Microlensing surveys have suggested that rogue planets may be far more common than previously thought. Some studies indicate that there could be billions or even trillions of rogue planets in the Milky Way alone. This means that free-floating planets may actually outnumber stars in the galaxy, making them a significant component of the cosmic population. The existence of such a large number of rogue planets has important implications for our understanding of planetary formation. It suggests that planetary systems are not always stable, and that gravitational interactions can frequently lead to the ejection of planets into interstellar space. This dynamic process may be a natural part of how planetary systems evolve over time. Rogue planets also challenge our understanding of what it means for a planet to be habitable. Traditionally, habitability has been defined in terms of a planet's distance from its star, specifically whether it lies within the habitable zone where liquid water can exist on the surface. However, rogue planets show that habitability may not be limited to star-dependent environments. Instead, internal heat sources and subsurface environments may provide alternative pathways for life. The internal structure of rogue planets can vary widely depending on their size and composition. Some may be rocky, similar to Earth or Mars, while others may be gas-rich, like Neptune or Jupiter. Gas giant rogue planets would likely have thick atmospheres and strong internal pressure, which could help retain heat more effectively than smaller rocky planets. Rocky rogue planets, on the other hand, may cool more rapidly, but could still maintain subsurface oceans if they are large enough. Another important factor is the presence of radioactive elements within the planet's interior. Elements such as uranium, thorium, and potassium produce heat through radioactive decay over long timescales. This process can provide a steady internal energy source that persists for billions of years. On Earth, radioactive decay contributes significantly to geothermal heat, and similar processes could occur on rogue planets, potentially sustaining subsurface environments for extended periods. The surface conditions of rogue planets are likely to be extremely hostile. Temperatures in interstellar space are only a few degrees above absolute zero, meaning that any exposed water or atmosphere would freeze almost instantly. The surface would likely be covered in thick layers of ice or frozen gases, creating a dark and inactive exterior. However, beneath this frozen surface, conditions could be very different, especially if internal heat is sufficient to maintain liquid layers. In addition to internal heat, some rogue planets may also experience occasional external heating events. For example, if a rogue planet passes near a star or a dense region of gas and dust, it could temporarily gain energy from external sources. These events would be rare and short-lived, but they could potentially influence the thermal evolution of the planet. The motion of rogue planets through the galaxy is also an interesting aspect of their behavior. Without a star to orbit, they follow independent trajectories shaped by the gravitational field of the galaxy. Over time, their paths may be altered by interactions with stars, black holes, or other massive objects. However, these interactions are generally weak compared to the forces that govern planetary orbits within star systems. Some rogue planets may eventually be captured by stars, becoming part of new planetary systems. If a rogue planet passes close enough to a star, it may be drawn into orbit and become a permanent member of that system. This process of capture is rare but possible, meaning that planetary systems can potentially acquire new planets long after their initial formation. The study of rogue planets also has implications for the overall mass distribution of the galaxy. If rogue planets are as numerous as some estimates suggest, they could represent a significant fraction of the galaxy's total mass. This hidden population of planets would be difficult to detect directly, meaning that much of the galaxy could be filled with unseen planetary bodies drifting through space. From a philosophical perspective, rogue planets represent a form of cosmic isolation. They are worlds without suns, without seasons, and without external energy sources. They exist in a state of perpetual darkness, moving through the galaxy with no fixed destination. In many ways, they represent one of the most extreme environments in the universe, where conditions are defined entirely by internal processes rather than external influences. Yet despite their isolation, rogue planets also represent possibility. They demonstrate that planetary bodies can exist independently of stars, and that habitable environments may not be limited to regions near stellar radiation. This expands the scope of astrobiology and encourages scientists to consider a wider range of environments in the search for life. As detection techniques improve, future missions may be able to identify and study rogue planets in greater detail. Advanced infrared telescopes or gravitational lensing surveys could reveal their distribution, composition, and internal structure. These observations could help determine how common they are and whether any of them might harbor subsurface oceans or other habitable environments. Rogue planets occupy a unique place in the cosmic landscape. They are neither part of traditional planetary systems nor completely isolated from the galaxy. Instead, they are wandering worlds, shaped by both their origins and their journeys through interstellar space. They expand our understanding of what a planet can be and challenge our assumptions about where life might exist. As we continue to explore the diversity of exoplanets, rogue planets remind us that the universe is not limited to systems centered around stars. It also contains vast populations of hidden worlds drifting in darkness, each with its own history and potential. The next step in this journey takes us to even more extreme planetary environments, where conditions reach the limits of temperature, radiation, and physical possibility. As astronomers continue to explore the diversity of planets beyond our solar system, they encounter worlds that exist under conditions so extreme that they challenge the limits of planetary physics. Among these are lava worlds, frozen giants, and other exotic planets shaped by intense heat, deep cold, or overwhelming atmospheric pressure. These extreme exoplanets reveal how far planetary environments can deviate from Earth-like conditions while still remaining stable celestial bodies governed by the same fundamental laws of physics. One of the most striking categories in this group is lava worlds. These are planets so close to their host stars that their surfaces are heated to temperatures high enough to melt rock. On such worlds, there are no solid continents in the traditional sense. Instead, the surface is likely a vast, dynamic ocean of molten lava, constantly shifting under the influence of stellar radiation, tidal forces, and internal geological activity. Lava worlds are typically found in extremely close orbits around their stars, often completing a full orbit in just a few hours or days. At such distances, the energy received from the star is so intense that it overwhelms the planet's ability to cool. The day side of the planet, constantly facing the star in many cases due to tidal locking, may reach temperatures high enough to vaporize rock-forming minerals. Elements such as iron, magnesium, and silicon can exist in gaseous form in the upper atmosphere before cooling and condensing on the night side. The boundary between the day side and night side of a lava world is often a region of extreme contrast. While the day side is dominated by molten rock and vaporized minerals, the night side may be significantly cooler, allowing some materials to solidify. This creates a cycle where material evaporates on the hot side, is carried by atmospheric winds to the cooler side, and then condenses and falls back to the surface. This process can lead to unusual geological and atmospheric dynamics not seen on any planet in our solar system. The atmospheres of lava worlds are often rich in heavy elements and metal vapors. Unlike Earth's atmosphere, which is dominated by nitrogen and oxygen, these exotic atmospheres may contain sodium, potassium, silicon monoxide, and other vaporized rock components. These elements can produce unique spectral signatures, allowing astronomers to detect and study these planets even from vast distances. Another key feature of lava worlds is the presence of extreme weather systems. While Earth experiences weather driven by water cycles, lava worlds may experience weather driven by rock vaporization and condensation. High-speed winds can transport vaporized rock across the planet, leading to dramatic temperature gradients and dynamic atmospheric circulation patterns. In some cases, these winds may reach supersonic speeds due to the extreme temperature differences between the day side and night side. The geological processes on lava worlds are also fundamentally different from those on Earth. Instead of solid crusts moving over a mantle, the entire surface may be in a constant state of flux. Molten rock flows continuously, reshaping the surface on short timescales. Volcanic activity, if present, would not resemble localized eruptions, but rather continuous global resurfacing driven by intense heat. Despite these extreme conditions, lava worlds provide valuable insight into planetary formation and evolution. They represent a class of planets that have undergone extreme orbital migration, moving inward from cooler regions to their current close proximity to their stars. Studying them helps scientists understand how planetary systems evolve dynamically over time and how planets respond to intense stellar radiation. At the opposite end of the temperature spectrum are frozen giants. These are planets that exist in extremely cold environments, either because they are located far from their stars or because they receive very little external heat. Frozen giants are typically large planets, often similar in size to Neptune or even Jupiter, but with atmospheres and surfaces dominated by ice and frozen gases. In frozen giants, temperatures are so low that gases such as methane, ammonia, and even hydrogen can condense into liquid or solid forms. The upper atmospheres of these planets may contain clouds of frozen methane or ammonia crystals, creating layered atmospheric structures unlike anything observed on warmer planets. Deeper within the atmosphere, pressure increases significantly, potentially leading to exotic states of matter where gases behave like dense fluids. The interiors of frozen giants are thought to be complex and layered. Beneath the outer frozen atmosphere, there may be regions of high-pressure ice, liquid water, or even exotic forms of ice that exist only under extreme conditions. At even greater depths, rocky or metallic cores may exist, surrounded by thick envelopes of compressed material. One of the most interesting aspects of frozen giants is the possibility of subsurface oceans. Even though the surface is extremely cold, internal heat from radioactive decay or residual formation energy may be sufficient to maintain liquid water beneath thick ice layers. These subsurface oceans could potentially exist for billions of years, shielded from the harsh conditions of space by insulating ice shells. In our own solar system, moons such as Europa and Enceladus provide examples of icy worlds that may harbor subsurface oceans. Similar environments could exist on exoplanets or large moons orbiting frozen giants in other star systems. These hidden oceans represent potential habitats for life in environments completely different from Earth's surface. Frozen giants also exhibit unique atmospheric behavior. Because of their low temperatures, atmospheric circulation is driven by slow but large-scale movements of gases and ices. Seasonal changes, if they exist, may occur over extremely long timescales due to the distant or weak influence of their host stars. In some cases, atmospheric layers may become stratified, with different gases condensing at different altitudes. Another category of extreme exoplanets includes those subjected to intense radiation from their host stars or other cosmic sources. These radiation-blasted worlds may experience continuous bombardment of high-energy particles and ultraviolet radiation. Over time, this radiation can strip away atmospheres, alter chemical compositions, and reshape planetary surfaces. In some cases, planets exposed to extreme radiation may develop protective magnetic fields that help shield their surfaces. However, if the radiation is too intense, even strong magnetic fields may not be sufficient to prevent atmospheric loss. This can lead to the gradual erosion of a planet's atmosphere, leaving behind a barren rocky core. The study of extreme exoplanets is important because it helps define the boundaries of planetary stability. By observing worlds that exist under conditions far more extreme than Earth, scientists can better understand the range of environments in which planets can exist. This, in turn, provides insight into how common or rare Earth-like conditions might be in the universe. Extreme exoplanets also play a key role in testing theories of atmospheric physics and planetary geology. The conditions found on lava worlds, frozen giants, and radiation-exposed planets push physical models to their limits, revealing new behaviors and interactions that are not observed under more moderate conditions. For example, the behavior of materials at extremely high temperatures or pressures can differ significantly from laboratory conditions on Earth. On lava worlds, rock vaporization and condensation processes occur on a global scale, while on frozen giants, gases may behave like liquids or solids under extreme compression. These environments provide natural laboratories for studying matter under conditions that are difficult or impossible to replicate on Earth. The diversity of extreme exoplanets also highlights the importance of orbital dynamics in shaping planetary environments. A planet's position relative to its star, its orbital eccentricity, and its interactions with other planets can all contribute to extreme conditions. Small changes in orbital parameters can lead to dramatic differences in surface temperature and atmospheric behavior. Some extreme planets may even transition between different states over time. For example, a planet that migrates closer to its star may transform from a frozen giant into a lava world, while one that moves farther away may cool and develop icy conditions. These transitions demonstrate that planetary environments are not static, but can evolve significantly over geological timescales. The study of these worlds also expands our understanding of potential habitability. While lava worlds and radiation-blasted planets are unlikely to support life as we know it, frozen giants with subsurface oceans may offer hidden environments where life could exist. This suggests that habitability may not always be defined by surface conditions, but by internal environments that are shielded from external extremes. As observational technology continues to improve, scientists will be able to study extreme exoplanets in greater detail. Future telescopes may detect atmospheric compositions, temperature distributions, and even surface or subsurface structures with higher precision. These observations will help refine models of planetary formation and evolution. Extreme exoplanets represent the outer boundaries of planetary diversity. They show that planets can exist under conditions that stretch the limits of heat, cold, radiation, and pressure, yet still remain stable objects governed by gravity and physics. These worlds expand our understanding of what is possible in the universe and prepare us for the next stage of discovery, where scientists will explore not just the physical extremes of planets, but the chemical and atmospheric signatures that may hint at the presence of life itself. Among all the frontiers in exoplanet science, none is more revealing or more complex than the study of atmospheres. While discovering planets is a major achievement in itself, understanding what these worlds are actually like requires looking beyond their size, mass, and orbit. The atmosphere is the interface between a planet and the rest of the universe, a thin but critical layer that controls temperature, weather, chemistry, and in some cases, the potential for life. By studying exoplanet atmospheres, scientists are beginning to move from simple detection toward deep characterization of alien worlds. On Earth, the atmosphere is essential for life. It provides oxygen for respiration, regulates temperature through greenhouse gases, protects the surface from harmful radiation, and enables weather systems that distribute heat and moisture around the planet. Without an atmosphere, Earth would be a barren and frozen rock. This makes atmospheres one of the most important factors when evaluating whether a distant planet could be habitable. The challenge with exoplanet atmospheres is that they are incredibly difficult to observe directly. These planets are light years away, and even the largest telescopes cannot resolve them as visible disks. Instead, scientists rely on indirect methods that analyze how light interacts with the planet's atmosphere as it passes through or around it. These techniques have become one of the most powerful tools in modern astronomy. One of the primary methods used to study exoplanet atmospheres is transmission spectroscopy. This technique is based on observing a planet as it passes in front of its host star, an event known as a transit. During a transit, a small portion of the star's light filters through the planet's atmosphere before reaching Earth. Different gases absorb different wavelengths of light, leaving behind a unique spectral fingerprint. By analyzing these patterns, scientists can identify the chemical composition of the atmosphere. For example, if a planet's atmosphere contains water vapor, it will absorb specific wavelengths of infrared light. If methane is present, it will leave a different signature. Carbon dioxide, oxygen, sodium, and other gases all have distinct absorption patterns. By carefully studying these signatures, scientists can build a picture of what the atmosphere is made of, even from vast distances. Another important technique is emission spectroscopy. This method is used when a planet passes behind its star, an event known as a secondary eclipse. During this time, the combined light of the star and planet is briefly reduced, allowing scientists to isolate the planet's thermal emission. By analyzing this emitted light, researchers can determine the temperature and composition of the planet's atmosphere. In some cases, scientists also use phase curve observations, which track the changes in brightness of a planet as it orbits its star. These variations can reveal information about temperature differences between the day side and night side of the planet, as well as atmospheric circulation patterns. Together, these methods provide a growing understanding of exoplanet atmospheres in remarkable detail. One of the most significant discoveries in atmospheric science is the detection of water vapor in exoplanet atmospheres. Water is a key ingredient for life as we know it, and its presence in an atmosphere is an important indicator of potential habitability. Water vapor has been detected in a variety of exoplanets, including hot Jupiters, mini-Neptunes, and some super-Earths. However, the presence of water alone does not guarantee that a planet is habitable, as temperature and pressure conditions may still be extreme. In addition to water, scientists have also detected a wide range of other molecules in exoplanet atmospheres. These include carbon dioxide, carbon monoxide, methane, ammonia, and sodium. Each of these gases provides clues about the planet's formation history, temperature, and potential chemical processes occurring within the atmosphere. For example, methane and carbon dioxide together can indicate active geological or chemical cycles. One of the most exciting goals in atmospheric science is the search for biosignatures, which are chemical indicators that may suggest the presence of life. On Earth, life has dramatically altered the composition of the atmosphere. Oxygen, for instance, is highly reactive and would not persist in large quantities without continuous biological production. The simultaneous presence of oxygen and methane in an atmosphere, especially under certain conditions, could suggest biological activity. However, interpreting biosignatures is extremely complex. Many non-biological processes can produce similar chemical signatures. For example, volcanic activity, photochemical reactions, and atmospheric escape processes can all influence the composition of a planet's atmosphere. As a result, scientists must carefully analyze multiple lines of evidence before drawing conclusions about potential life. The study of exoplanet atmospheres also reveals incredible diversity. Hot Jupiters, for instance, often have extremely dynamic and exotic atmospheres. Due to their close proximity to their host stars, these planets experience intense heating on their day side, leading to extreme temperature differences between the illuminated and dark hemispheres. This drives powerful atmospheric winds that can redistribute heat across the planet. In some hot Jupiters, wind speeds can reach several kilometers per second. These winds can transport heat and chemical compounds around the planet, creating complex and turbulent weather systems. Some models suggest that clouds on these planets may consist of vaporized metals such as iron or titanium, which condense in cooler regions of the atmosphere. Super-Earths and mini-Neptunes also exhibit diverse atmospheric properties. Depending on their size, composition, and distance from their star, these planets may have thick hydrogen-rich atmospheres, dense carbon dioxide-dominated atmospheres, or even water vapor-rich envelopes. Some may have hazy atmospheres filled with photochemical smog, while others may have clearer skies depending on their chemical composition and stellar radiation environment. Another fascinating class of atmospheres belongs to lava worlds and ultra-hot planets. On these extreme worlds, temperatures are so high that rock itself can vaporize. The atmospheres of such planets may contain elements like sodium, potassium, silicon monoxide, and even traces of iron vapor. These atmospheres are not stable in the long term and may continuously cycle between vaporization and condensation depending on temperature variations. Frozen giants and cold exoplanets present the opposite extreme. In these environments, atmospheric gases may freeze into clouds of ice crystals or condense onto the surface. Methane, ammonia, and nitrogen can exist in solid or liquid forms depending on temperature and pressure conditions. Atmospheric dynamics on these planets are slow but complex, shaped by long-term seasonal changes and deep internal processes. One of the most important advances in atmospheric science has been the ability to study temperature profiles of exoplanets. By analyzing how temperature changes with altitude in an atmosphere, scientists can understand how energy is distributed within the planet. Some exoplanets show thermal inversions, where temperature increases with altitude in certain atmospheric layers. These inversions can be caused by the presence of absorbing molecules or strong stellar radiation. Clouds also play a major role in shaping exoplanet atmospheres. On Earth, clouds influence weather and climate by reflecting sunlight and trapping heat. On exoplanets, clouds can be made of a wide variety of materials depending on temperature and pressure. These include water vapor, methane, ammonia, silicates, and even metals in extreme cases. Clouds can obscure spectral signatures, making it more difficult to analyze atmospheric composition. Despite these challenges, scientists are developing increasingly sophisticated models to interpret atmospheric data. These models combine physics, chemistry, and observational data to simulate the behavior of exoplanet atmospheres under different conditions. By comparing these models with actual observations, researchers can refine their understanding of distant worlds. The study of exoplanet atmospheres is also closely linked to planetary evolution. Atmospheres can change dramatically over time due to processes such as atmospheric escape, volcanic activity, and chemical reactions driven by stellar radiation. Some planets may lose their atmospheres entirely, while others may develop thick and complex layers over billions of years. One of the key processes affecting atmospheres is atmospheric escape. High-energy radiation from a star can heat the upper layers of a planet's atmosphere, causing gases to escape into space. This process is especially important for smaller planets or those orbiting close to active stars. Over time, atmospheric escape can significantly alter a planet's composition and potential habitability. The study of atmospheres also provides insight into planetary climate systems. By understanding how heat is distributed across a planet, scientists can infer the presence of winds, jet streams, and circulation patterns. Some exoplanets may have global weather systems that are entirely different from anything seen on Earth, driven by extreme temperature gradients or unusual atmospheric compositions. As technology continues to advance, the next generation of telescopes will revolutionize the study of exoplanet atmospheres. Instruments such as space-based observatories will be capable of directly imaging some exoplanets and analyzing their atmospheres with unprecedented detail. This will allow scientists to move beyond detecting molecules and toward understanding full climate systems and potential surface conditions. The study of exoplanet atmospheres represents a crucial step in the search for life beyond Earth. It bridges the gap between simple detection and true understanding of alien worlds. By analyzing the thin layers of gas surrounding distant planets, scientists are beginning to uncover the chemical and physical processes that shape planetary environments across the galaxy. As we continue this exploration, atmospheres will remain one of the most powerful tools for understanding exoplanets. They carry the signatures of planetary history, climate, and potential biology. In the next stage of discovery, attention turns toward the ultimate question, whether any of these atmospheric signatures point not just to chemical activity, but to the presence of life itself. The search for life beyond Earth represents one of the deepest scientific questions humanity has ever pursued. After mapping thousands of exoplanets, studying their sizes, orbits, compositions, and atmospheres, the focus of modern astronomy is gradually shifting toward a single profound goal: to determine whether life exists elsewhere in the universe. This is not only a question of biology, but also of chemistry, physics, and planetary evolution. It requires understanding how planets form, how environments change over time, and how complex chemistry can arise under different cosmic conditions. Life on Earth provides the only known example of biology in the universe. Every observation we have of life is based on a single planetary environment, shaped by Earth-specific conditions. Liquid water, a stable atmosphere, a moderate temperature range, and a long-term stable energy source have all played essential roles in the development of life here. However, the discovery of thousands of exoplanets has revealed that Earth is only one of many possible planetary environments, and that the conditions for life may exist in far more diverse forms than previously imagined. The search for life begins with identifying habitable environments. This is why exoplanets in habitable zones, ocean worlds, and planets with Earth-like atmospheres are of such great interest. However, habitability alone is not enough. A planet may have the right temperature for liquid water, but still lack the chemical ingredients or stability required for life. Understanding the full range of conditions that could support biology is one of the central challenges of astrobiology. One of the most important concepts in this search is the idea of biosignatures. A biosignature is any chemical, physical, or atmospheric feature that could indicate the presence of life. On Earth, life has profoundly altered the atmosphere and surface chemistry of the planet. The presence of oxygen, methane, and other reactive gases in specific combinations is largely the result of biological activity. If similar patterns are detected on exoplanets, they could suggest the presence of life, although careful analysis is required to rule out non-biological explanations. The most widely discussed biosignature is oxygen, particularly when found in large quantities in a planet's atmosphere. On Earth, oxygen is continuously produced by photosynthetic organisms. However, oxygen can also be generated through non-biological processes such as the breakdown of water by ultraviolet radiation. Therefore, oxygen alone is not definitive proof of life. It must be considered alongside other gases and environmental conditions. Methane is another important gas in the search for life. On Earth, methane is produced by both biological and geological processes. When methane is found together with oxygen in a stable atmosphere, it creates a chemical imbalance that is difficult to maintain without continuous replenishment. This disequilibrium is one of the strongest potential indicators of biological activity. If similar combinations are found on exoplanets, they could represent some of the most promising evidence for life beyond Earth. Water remains central to all discussions of habitability and life. It is a unique substance with properties that make it ideal for supporting chemical reactions necessary for biology. Liquid water acts as a solvent, allowing molecules to interact and form complex structures. Many exoplanets have been found with water vapor in their atmospheres, and some may have vast oceans covering their surfaces. However, the presence of water alone does not guarantee life. It simply provides a necessary condition, not a sufficient one. One of the most intriguing possibilities is that life may exist in environments very different from Earth. While all known life on Earth depends on water, it is possible that other solvents, such as ammonia or methane, could support alternative forms of biology under different conditions. This expands the scope of the search significantly, allowing scientists to consider a much wider range of planetary environments. Ocean worlds are particularly important in this context. These planets may be completely covered by deep global oceans, potentially providing stable environments for life to develop. On Earth, life likely originated in aquatic environments, such as shallow seas or hydrothermal vents. On ocean worlds, similar processes could occur in much larger and more uniform environments. However, the lack of land and geological diversity may limit the availability of certain nutrients, which could influence the complexity of any potential biospheres. Subsurface environments are another key area of interest. Even if a planet appears inhospitable on its surface, conditions beneath the surface may be very different. On Earth, microbial life has been found deep underground, in rocks and beneath ice sheets. These organisms survive without sunlight, relying instead on chemical energy from geological processes. If similar subsurface environments exist on other planets or moons, they could provide hidden habitats for life. In the outer solar system, moons such as Europa and Enceladus have already shown evidence of subsurface oceans beneath icy crusts. These environments are heated by tidal forces generated by their parent planets, creating conditions where liquid water can exist despite being far from the sun. If similar mechanisms exist on exoplanets or exomoons, they could significantly expand the number of potentially habitable environments in the galaxy. Another important concept in the search for life is atmospheric disequilibrium. On Earth, the atmosphere is far from chemical equilibrium due to biological activity. Life constantly alters the composition of the atmosphere by producing and consuming gases. If similar disequilibrium is detected on an exoplanet, it could suggest the presence of active biological processes. However, distinguishing between biological and non-biological sources of disequilibrium is extremely challenging and requires careful analysis. Technological advancements are playing a crucial role in this search. Space telescopes are becoming increasingly powerful, allowing scientists to analyze exoplanet atmospheres in greater detail than ever before. By studying the light from distant stars as it passes through or reflects off planetary atmospheres, researchers can detect the presence of key molecules and begin to reconstruct the environmental conditions of these worlds. Future telescopes will be capable of even more precise measurements. They may be able to directly image Earth like exoplanets and analyze their atmospheres with high resolution. This will allow scientists to search for subtle chemical signatures, seasonal changes, and even surface features that could indicate the presence of oceans, continents, or vegetation. One of the most ambitious goals in exoplanet science is the detection of what is sometimes called a true Earth analogue. This would be a planet similar in size, composition, and temperature to Earth, orbiting a Sun-like star in a stable, habitable zone. Finding such a planet would be a major milestone in the search for life, although even such a discovery would not guarantee that life exists there. It would simply identify a world with conditions similar to those that support life on Earth. Beyond individual planets, scientists are also interested in understanding how common life might be in the universe. This involves estimating the frequency of habitable planets, the likelihood of life emerging under suitable conditions, and the probability of life developing into complex or intelligent forms. These questions are deeply uncertain, but exoplanet discoveries are gradually providing the data needed to refine these estimates. The diversity of exoplanets discovered so far suggests that planetary systems are highly varied. This diversity may increase the likelihood that some environments are suitable for life, even if they differ significantly from Earth. Life on Earth is adapted to a specific set of conditions, but there is no reason to assume that life elsewhere must follow the same rules. In addition to chemical and environmental signatures, scientists are also considering the possibility of detecting technological signatures, sometimes referred to as techno-signatures. These could include artificial radio signals, atmospheric pollution caused by industrial activity, or even large-scale structures that alter the light from a star. While no confirmed technosignatures have been detected, the search continues alongside traditional biosignature studies. The search for life is not limited to any single type of planet. It includes hot worlds, cold worlds, ocean worlds, rocky planets, and even rogue planets drifting through interstellar space. Each of these environments offers different possibilities for how life might emerge and survive. The universe may contain many forms of life that are very different from those found on Earth, adapted to conditions we are only beginning to understand. As we continue to explore exoplanets, each new discovery adds to a growing picture of a universe filled with diverse and dynamic worlds. Some may be barren and lifeless, shaped only by physical and chemical processes. Others may harbor conditions suitable for life, hidden beneath clouds, oceans, or ice. A few may even contain active biospheres, quietly evolving under alien skies. The journey to find life beyond Earth is still in its early stages, but it is rapidly advancing. With each new telescope, each new survey, and each new discovery, we move closer to answering one of the most profound questions in human history. Are we alone in the universe, or is life a common outcome of planetary evolution across the cosmos? The search continues, not just as a scientific endeavor, but as a reflection of humanity's desire to understand its place in the universe. Every exoplanet discovered, every atmosphere analyzed, and every potential biosignature examined brings us one step closer to understanding whether life is a rare accident or a widespread feature of the cosmos.